Multiparadigm Data Science with the Wolfram Language. Section 4. Assembling a multiparadigm toolset. In navigating the analyze stage of our question-driven multiparadigm workflow, we've looked at questions of the type, is this A or B? Or how much of something or how many items can we expect? How is the data structured? Are there inherent groups to which the data samples belong? And so on. Next, let's take on the question, is this weird or unusual? When faced with some data, can we identify the samples that seem to stand out for whatever reason? The unsupervised machine learning technique of anomaly detection is what we would use in such a case. So anomaly detection would be the tool to use if we were attempting to spot an attack amidst regular network traffic, or identify a fraudulent transaction on a stolen credit card amidst the usual transactions of a regular customer, or spot the unusual characteristics of a diseased cell amidst healthy tissue samples. Outliers or anomalies are data points that are very different from most other data points. They are rarer. We can find such anomalous elements in data using FindAnomalies. Internally, FindAnomalies depends on the learn distribution function we covered in the previous segment, which tries to learn the underlying distribution of the data given a set of examples. Learn distribution and FindAnomalies works with any type of data, not just numbers. Given the underlying distribution of the data, FindAnomalies finds the data points that are outliers in the sense that they should occur only with very low probability according to the learned distribution. Rarer probability computes the probability for a distribution to generate a sample with a lower PDF than the examples provided. The acceptance threshold option can be used with FindAnomalies to specify the value of rarer probability that should be considered very small and therefore cause samples being labeled as anomalies. Let's revisit the Fisher-Iris dataset and try to use anomaly detection on the samples. The detector function can be used to identify outliers from a dataset, or it can be used to provide a verdict, anomaly or not, for individual samples. Rarer probability is used to decide which examples are outliers. By default, any example with a rarer probability smaller than 0.001 is considered an outlier. But we can change this threshold and thus change the outlier decision boundary for the data. Here is another example demonstrating how anomaly detection can be used on a classic dataset containing both numerical and nominal variables. We have to use dimension reduction to allow us to visualize both the data and the anomalies in a scatter plot. Observe how the decision of whether a sample is an anomaly or not changes with a change in the acceptance threshold for FindAnomalies. Anomaly detection can easily work on time series data as well. For example, here is a time series of dates and daily closing values of the S&P 500 index since January 1st, 2015. We can partition this data into a list of consecutive windows and use FindAnomalies to detect unexpected changes in the sequence. Here are the detected anomalies overlaid on the original time series. If we are worried about outliers or anomalies throwing the entire analysis off track, DeleteAnomalies can be used to both find and remove the anomalous samples from the data in one step. In the wrangle stage of the workflow, we looked at dealing with messy data and briefly discussed the possibility of using machine learning to compute replacements for missing data. The unsupervised learning task of learning a distribution from the data can be used to synthesize replacements for missing values. In this example, we can use SynthesizeMissingValues as a custom image in Painter. We can first learn a distribution for the pixel values from the available images and then use it to generate replacement values for the missing data in new samples. Along with the different questions we've looked at so far in the analysis stage of the question-driven multi-paradigm project workflow, there's one we need to consider specifically for sequential data. Given a sequence of observations adhering to an imposed order, we may want to know what comes next in the sequence. For example, say we want to create a text generator that writes in the style of a particular author, maybe Charles Dickens. The way to do this would be to train a sequence predictor on the works of Charles Dickens, say Tale of Two Cities, and then once trained, we can give a starting sequence to the predictor and ask it to generate text that is most likely to come next in the sequence. Of course, the predictions completely depend on the training data, and so if we train our text generator on Pride and Prejudice instead of Tale of Two Cities, we can expect it to generate text sequences in Miss Austen's style of writing. SequencePredict in the Wolfram language internally uses the Markov model, and we can set the order of the Markov model in the method suboption. Here, the order was set to 3 automatically. Increasing it to 5 does not necessarily seem to improve the quality of the prose. The Wolfram language also has a few built-in sequence predictors trained on text in various languages that can generate pseudotext in these languages. Here's one example for the German sequence predictor. And sequence prediction works just not for text but also for other data. SequencePredict allows the modeling of any kind of sequence in order to predict its future evolution. For example, here is a data set with samples of sequences of a player's moves in rock, paper, scissors. SequencePredict can be used to predict the next action of the player, whether they are going to play rock or paper or scissor, given his previous actions. Now let's look at a special type of sequential data which have an imposed order in time, generally known as time series, and we've looked at a few examples of time series data earlier in this course. The financial data function in the Wolfram language returns such time series objects which are really time value pairs of stock prices or exchange rates of currencies along with the corresponding dates, so the data is ordered in time. These are the daily exchange rates of the euro to USD from October 2018 to March 2019. Since the rates are available only for business days, we need to resample to ensure the time increment is indeed a business day and there are no gaps in the data for the weekends. We can fit an autoregressive process on the time series data from the past and use it to forecast the rates for 20 business days in the future. Here is a comparison of the training data, the forecast, and the actual values for the dates used for the forecast. Let's look at another example attempting to forecast the temperature in Champaign, Illinois, based on the monthly temperatures of past 10 years. Instead of estimating a process, we can directly try to fit a time series model on the data. This is the temperature in Champaign as predicted by the model today. By the way, this is really the temperature for today. Here are the forecasted temperatures for 2019. We can use the various properties of the model to get more information. In summary, we looked at 2 more questions that could drive our multi-paradigm project workflow in this segment. 1, is this unusual? And 2, what comes next. To find out if a data point is unusual, an anomaly, or an outlier, we can use FindAnomalies, which internally uses learned distribution. We looked at a few examples of using FindAnomalies for numeric and time series data. We also looked at DeleteAnomalies for finding and deleting anomalies. As a quick aside, we also looked at SynthesizeMissingValues as another use of learned distribution function to generate replacement values for missing data. To answer the question, what comes next, we looked at sequence prediction and time series forecasting. So in all, we have looked at few different questions we can ask to get started with the Multiparadigm Data Science project and the associated multiparadigm tools that can help us answer these questions. After looking at one more tool that has become very popular for applying machine learning in data science, neural networks, we will be ready to move on to the last stage of our project workflow, communicate, to get the message across at the end of the project workflow.